here and there, these would definitely be of use. If people can take away from these webinars the way to present, even tips on what to talk, some examples to quote, all that would also be very good and something which we can always cherish. From Rajalakshmi Engineering College. Yes, Mr. Devanathan. Welcome, sir. I used to know your computer science head, Dr. Sheila Anand. She was my colleague we used to work in Osaka together. You can unmute and speak. Very happy to see that engineering college people are also participating in this Polytechnic initiated webinar. Mic is a problem, sir? Okay, no problem. Welcome, welcome. We're so happy to have all of you here. Suresh Kumar from Ramco Institute of Technology, Rajapalayam. Welcome, sir. You are again an NBA accredited college, so we have been trying to benchmark ourselves against many of your good practices. Welcome. Thank you. So we'll start with the introduction. We'll start on time so that we end on time as well. Yes. Thank you, Dr. Joshua. And once again, a very, very warm welcome to all the participants, the delegates, the teachers in Polytechnic and engineering colleges, our dear students, and my dear friend, Dr. Tirupati, for having accepted this invitation and actually giving us the privilege of hearing him or listening to him in this webinar series. In fact, I only sent him an WhatsApp message and he immediately accepted it. So that is his generosity. It will be my proud privilege to introduce and read out his short profile. He has a doctorate in sustainable manufacturing from Production Engineering Department, NIT, Trichy, in 2019. So it is an inspiration for all of them who think that age is a barrier for pursuing higher studies. So I really salute the way you have pursued your doctorate at this age and you've completed it. Masters in Technology from IIT Madras in Mechanical Engineering in 1987 and Bachelor's degree from Annamalai University in 1985 in Mechanical Engineering. He is currently employed in Rane TRW Steering Systems Private Limited, Steering Gear Division, a 50-50 joint venture between Rane Group and IZDF as Senior Vice President, Product Engineering, responsible for product engineering and supports project management. He has previously worked at BEML, Bharat Earth Movers Limited, KGF, in R&D division in vehicle area and hydraulic products. He has worked in design and introduction of several product lines for commercial vehicles, tractors, and passenger car segments during his 27 years experience at Rane TRW. He has a US patent granted in steering gear design, 11 patent applications in Indian Patent Office. He has won several awards for innovation and product design from Rane Group, ACE Award 2017, various innovation awards from leading auto magazines. He is currently working on several product innovations in steering products to bring indigenous technology in mainstream production for Indian OEM in commercial vehicles and farm tractors. He is a member of professional bodies like Institution of Engineers India. Welcome, sir. We are very happy to have you amidst us. Looking forward for the next 1.5 hours of exciting session on design for reliability, a practitioner's approach. Handing over the session to Dr. Tirupati.
Yeah. Thank you, madam, for the kind words. I had been working with Rane for almost now 29 years. The resume what you read was actually I had sent last year. It was prepared for another polytechnic. So because of want of time, I could not update. Currently, I'm responsible for the advanced engineering. I want to bring it to the notice of the team because we may get some update earlier again. So good afternoon. I'm thankful to the Rane TAP management and Mrs. Rajalakshmi for providing me an opportunity to speak on the second day of the 3-day Top Tech Trends 2021. So somebody might be wondering, what is this design for reliability? Is it a top tech trend? Okay, not exactly a technical trend, but it has been there for the last several 100 odd years. But the need of the day is, as customers, we start expecting more and more from the product. So from that angle, I still thought it's a technical trend which, as a designers, as engineering guys, should be aware of, so that we keep our customers and the end users very happy. I've chosen this topic, design for reliability, a practitioner's approach. It is quite interesting area for me as a designer, and as well as to the quality management teams in any industry, and also worthwhile for the faculty to teach the design and quality aspects to the engineering the students. So I thought this will be really a great opportunity to exchange my ideas, and then probably you can, as Madam was explaining earlier, if some of you can take 1 or 2 of these inputs, and then you can pursue on your own in terms of your either research or quoting or examples for your real-time studies, it will be really, I thought, I would achieve my objective. So this is the content of my presentation. I may not be completing almost 1.5 hours. I think I would finish it by 1 hour 15 minutes. Maybe another 5-10 minutes we'll have it for some open question answers or some exchange of ideas. So I will start in terms of the company profile to give an idea about my mental thought process on why I'm talking such and such things. The other contents of the presentations include distinction between design and the reliability. Previously, design and reliability. Okay, so what is the difference? I've included some mathematics for the entirety of the presentation. I do not intend to dwell fully into that, because once you start mathematics, people will start feeling it is too much. Whether it's a student or any faculty. So I would not go deeper of that, but some of my learnings from Dr. Washio and even my own classwork during my academic during my PhD, I have used some of them, so I really understand what is expected from the faculties and as the researchers, so that it will be of very much useful when I talk some of them. The other things to know are the handy tool list, application of such tools in especially mechanical design and the products. No presentation on reliability will be complete without talking about calculation. Hence, I will be talking about the reliability prediction. So when we talk about prediction, we first have to calculate some example of a calculation, and we'll be showing it. And we'll go to slide number 3. Yeah. Slide number 3 talks about the human interface reliability. Reliability itself is an extension of quality, and as you all know that reliability is a quality over time. How the quality starts changing over time, and quality it is defined as what customer tell it is. It is very strange that there is no latest standard very clearly telling what quality is, but quality is what customer tell. If the customer tells is not good, then that's it. The product is not going to sell well. So it's very, very difficult to handle customers. So you have to be ahead of the customer's thought process. So some of the tools like QFD, quality function deployment, which is being really used for product design, also will be touched upon during the discussion in terms of how it can be used for reliability. Reliability need to be built, measured, and hence test for reliability is a topic, is a very equal importance. I'll be touching upon that. So I will not be going too much deep into that, to just give a bird's eye view of what's being done in the industry. I'll also talk about reliability for electronics. I have got some idea the last 4 years working on electronic products. I'll ask my colleague to handle that 10-minute session so that I get some time to recoup myself. Even though it is new to me, all mechanical products are getting into mechatronic versions due to intelligence being built in by the software. I think many of you are aware that the software is the latest thing which will be ahead of the gold in terms of market value. So obviously many youngsters are jumping into software, but in terms of mechanical products, they are too getting into the mechatronic version. So the software reliability is a separate area. However, I'm going to touch here only the electronic reliability part of it, because I think we still not graduated into the software reliability. That is totally a new area. Like functional safety standards are being required by the industry for certification. So that's totally a new topic. In fact, it's worthwhile to look at from that angle. I will also give some list of journals for entirety of the presentation. International journals on reliability, and also some of the conferences. Of course, there are some slides to be observed by you that we shown. And also talk about some of the commercial software list when you talk about reliability, calculation, prediction. So it's sometimes going to be useful to use a software than to use it a manual version. Even though Dr. Washu, our guru from Japan, is a Jusei scientist, he was giving always examples on by doing the hand calculation. But then he was also suggesting that if you have a software, we also had some people from Japan, Dr. Suzuki was an expert in reliability. We also had the good amount of inputs from him in the last, I think, 10, 12 years back. But we use some of those thought process in terms of improving our product design over a variety of models. So this is my content slide. So hope it is going to be useful for you. So please keep your attention on the slides. I'm going to be using the slides definitely as a reference. But then we can always have a discussion. If my energy permits, definitely I'll be more interested to explain in detail. Next slide, please. So this is slide number 4. I'm going to talk about a company, Rane TRW, a brief introduction. It's a steering gear manufacturing company. Was opened in 1985 and manufactures multiple products, most of them in the mechanical and hydraulic domain and the steering gear business. Okay. In terms of TRW was one of the Fortune 100 companies with multiple product lines, a long history of more than 110 plus years. It was divested, and finally in 2014, the steering business was acquired by ZF Germany. ZF is a strong transmission-based company with a trust or a foundation overseeing it. So you can understand that the philosophy of ZF has to be to make the best, to make the life of the people better. And I think that is what our Rane Trust is also trying to do. I think this example is very clear that we want to improve the life of many of these people in terms of what we can do for them. The typical German thinking is to make the best product in the world, and ZF always has been doing it in the same philosophy. Rane has a similar spirit in terms of doing the best in class product. Okay. So that is how RANE and the TRW still and RANE and ZF still makes a lot of sense to exist. So even during this year, we had a very close understanding between the top management of ZF and RANE. So the business partnership is going to continue for several years to come. Next slide. RANE TRW steering gear made a division made a turnover of 420 crores, something like close to $60 million in 2020-21, dropping from about I think $85 million in 2018-19. Obviously, it was the erosion in the commercial vehicle market volumes because of the introduction of the new norms of the FA BS6, which actually altered the customer's mindset and also increased the front axle weight and capacity of the vehicles. And the COVID situation also actually brought. However, we have several product lines that really helped us to keep us afloat in terms of having a good turnover of around 420 crores. Next slide, please. So this 86 million is 2018-19, but I have retained this slide because we have the similar turnover in terms of 53% of our product are commercial vehicle steering gears, and 30% hydraulic rack and pinion, and 17% is from the hydraulic pump. The discussion of this product clearly shows that the turnover has been almost been similar. Recently, we got a new business opportunity in terms of hydraulic tractor gear. It's actually a modification from the commercial vehicle steering gear, and we are in the process of getting several nominations for those products. Next, slide number 7. So here I have also shown the various customer awards and direction of the organization, the philosophy, the purpose of its existence for its stakeholders. So most of these awards are like best supplier, trusted supplier, quality award. It always been the expectation of the every individual in the organizations to make it the best in class commitment and honoring to the customers. And RANE TRW has been a proud member of this receiving award from the OEMs. Next slide, please. Quickly coming to the RANE TRW geographical locations, we talk about 4 locations, including Chennai and Trichy and Uttaranchal, and then in Guduvancheri. All the plants have IATF quality systems, IATF 16949, which is mandatory. Next slide. Yeah. So RANE TRW serves about 14 OEMs in the commercial vehicle product lines. We have 20 models and 100 variants of them. We used to deliver as high as 30,000 numbers. The installed capacity is 30,000 numbers per month in terms of the assembly. The warranty policy is very important for us to note here is that from the year 2020-21 onwards, the warranty policy is about 300,000 kilometers or 3 years. So compared to a past car, which is, I think people are talking about 200,000 kilometers and or 2 years. Commercial vehicle is definitely a very tough business because the customers use or abuse, whatever you call it, has been there. And of course, government is trying to bring more standards and trying to give legislation to both users as well as the OEMs, in fact, to suppliers like us. So products manufactured have a great influence on the customer feel, like steering. Steering is actually on the dashboard. So people can really, make the product or break the product. Like if they are not happy with the steering feel, they would start telling this is not a good product. Okay. So obviously product manufacturers have a great effect on customer feel. And having said that, it is nothing to be told less that it's very safety critical, because if the steering doesn't work, the vehicle is not in control. So product manufacturer is safety critical, has a high effect on the customer feel and satisfaction with respect to performance. And obviously in terms of the downtime too, because the product is not able to be driven or be being steered, customer is very upset. So we can understand the expectation of the product. So it's a very, very tough decision for a designer to take a decision in terms of the multiple challenges in terms of the safety criticality, the feel part of it, and the repair part of it. Like you can't afford to have downtime. I can't use a low quality design and then allow it to be. So this is really a very tricky area. So how we have been handling this for the last 2 decades, I have got some experience. Of course, TRW has been manufacturing products, steering gear products for more than 50 plus years. They started manufacturing in recall 1950s and 60s. So they have almost 40 plus years when we actually have the technology transfer in the earlier time. Next slide. Sorry, can I go ahead? Yeah, good. Yeah. So we are in slide number 10. I've shown here two pictures, basically to give a feel that why I am competent in terms of the electronic, the steering gear. The left side is a complete hydraulic steering gear, the right is electro-hydraulic steering gear. So I'm going to give some few practical ideas and tips on the electronic reliability and how we are doing it, how we are trying to tackle them in the Rani TRW. Okay, next slide, please. Okay, how do you differentiate design and reliability? It's very important for us to understand this before we go dwell deeper into the design for reliability. So this is a very classical definition. I pulled it from one of the literature. I've highlighted some of the aspects in terms of my understanding, what we cannot afford to forget. So obviously, if you have a product, we need to have a user. So user has a need. So user need, it has to be met by a shared objective during the entire product life cycle. So this is the three important words. The user needs in terms of the stated objective has to be met through the entire product life cycle. And obviously, as engineering people, we are using the help of mathematics and science to optimally convert the material to get the result out of the product. Now, reliability is the ability of the system to meet the stated objective in the stated condition for a specific period of time. Now, there are two things getting added: the stated conditions and the time period. So, if you're going to talk about reliability, I need to talk with respect to application. I need to talk for a particular time. So, this is very important because I was telling we are having a warranty of 300,000 kilometers. Okay, for a particular application. For example, the bus application actually are less severe compared to a truck application. So some of their customers are giving a larger warranty terms. They are given 5 lakh kilometers for bus applications, whereas truck they are giving 300,000 or 3 lakh kilometers. So it means for the stated conditions, for the stated time, the product has to work without any problem or without any nuisance. So that is what is the expectation of reliability. So Tamil Nambagatanmai, reliability is nothing but Nambagatanmai of the product. So you can believe the product that it will work for so many hours in so many conditions. I used to get the earlier discussions of reliability when people have to go in a car long time back, like in Ambassador or those times. So first they will check whether I have a spare battery or a spare bulb. Okay, because these are the things electrical. There's a problem. Okay, let me have a spare. Okay, this was the theory 40 years or 50 years back when we had only Ambassadors and this Maruti was getting into the market. So from that time onwards, definitely Maruti has defined as a new standard to the Indian industry. So in terms of its own reliability and product performance, and has been a benchmark in terms for the commercial vehicle too. Okay, so next slide, please. So I was talking about the product life cycle. Product life cycle is an important concept because if you look at that, about 85% of the cost is being sunk into the design in its lifetime during the design stage, like in the concept or at the system level, or for example, a commercial vehicle. When you talk about the system design, steering system design, 80% the cost is fixed. Like I want to go with a recirculating ball type design gear. So it means my cost is fixed. I can't make it less. So this is an important concept. The concept of design itself, 60% concept cost is fixed. For example, I want to go with electro-hydraulic gear or hydraulic gear. So 60% of the total cost is determined here. So what I'm trying to tell here is a very low amount of cost or influence can be done at the later stages of the product life cycle, like manufacturing or operations can do only 5 to 10% of improving the product quality or the product reliability. So very important that during the design, during the development, during testing, these things are taken care so that customers are very happy and really we have a repetitive selling product. We call it as a hit product. These products are selling at a high volume. Next slide, please. Okay, so I'm trying to tell what are the areas to be considered in the design for reliability issues. So these actually have a cause and effect. To go through a problem of a reliability problem and then try to group them. So what has gone wrong or what is the influence of which has actually caused the problem, which has been the cause for a reliability problem. So if you look at that and then try to group them, we find that starting with the CAD or FE or a database, then going to the prototype evaluation to engineering model evaluation, we have got different areas to be considered. I'm going to give an example, 10 examples in the last few minutes of my presentation to clearly give an idea of how people have been able to improve the design from a reliability point of view. So, for example, this might look repeating for you, derating, safety factors, redundant system, and then technical standards usage, engineering proto evaluation, model evaluation. So these have been not properly done in the earlier part of the work, causing really the concern in terms of the issue for the product to have a failure in the reliability. You can go to the next slide, please. Yeah. So when we talk about reliability, so one important thing we have to remember is a bathtub curve. So this really looks like a bathtub. We talk about three areas of this bathtub curve. One is a decreasing failure rate, okay, which is coming down, and that's a flat one called the constant failure rate, or we also call it a random failure. The other one is the increasing failure or wear out failure. So I'm going to talk in somewhat depth in coming slides. So you can think like it's like a bathtub. So many people think that all the products will work or fail in this way, but not necessarily. Some of them will have only the decreasing failure rates, and some of them will have only the constant failure rates, or some only the wear out failure, or some of them have a combination of all the three. So this can be obtained by means of doing the data collection from the field or from the lab, like subjecting some 10, 12 parts, or from the field you have to do the initial samples, and then at least 20 to 30 numbers you have to test. But it's a very expensive process. But in the overseas, when the volumes are really in millions, for example, in the past car, people used to test for 200 vehicles. In fact, we also had experience when we had multiple products being launched for various markets in the power rack and pinion division. It was simultaneously launched in 4 countries or in 4 continents. So it means they had to test in a lot of geographical conditions. They tested 200 odd vehicles, so they really got a good reliability data with which they can actually give the confidence to the customer in terms of what's the reliability they can give. Next slide, please. So we are in slide number 16. So this is a result of the solutions employed during the real time problem solving. So in my experience in running KW, typically the premature failures are taken care by taking consideration of the processing or manufacturing. So if we are able to improve the process quality or the incoming material quality, we can really bring down the initial failure rates is actually going to decrease. If you look at the failure rate graph, then you can understand that, for example, within 10,000 kilometers, if the failure rate is very high, it means it's very clear that it is something to do with the raw material or process. If it's up to 40,000 kilometers, then it is something with random failure. It also could be due to severe usage condition which was not being tested during initial design. So, for example, a better fillet could have been, required. A simple example is a solution, but then this could have not been, brought out in the initial design testing, because you would have not tested sufficient number in the field. In the wear out failure, we need to consider a better material of the design. For example, the material itself is getting worn out. For example, we have rubber, we have a nitrile rubber, so which is having a temperature limit of 120 degrees. And if you want to use a steel for 135 degrees for a long time, like 8 to 10 hours, then we have to go for even still better material from nitrile to hydrogenated nitrile, or even Viton type of rubber instead of an ordinary nitrile rubber. So this very clearly tells that we have to use highly reliable parts also could improve the wear out failure. In terms of random failure, it's very tricky because you may have to have different ideologies and philosophies to understand how that it's not being captured during the design stage. Sometimes you can use the redundant system or highly reliable design, highly reliable parts itself. I'm going to give some example in the last. Next slide, please. So design for reliability in random failure, I was telling this is slightly more difficult to handle. So simplification, standardization, and then design margins and redundantization also are important. So in terms of simplification, use of design standards for manufacturing. For example, there's always a difficulty whether to use a standard part or make it to the print. For example, I want to make a fastener. Okay, I want to make a bolt. So should I use a standard fastener, or should I make it to a special part to my own standards of material and thread fit, and also to the heat treatment aspect? So this is slightly difficult, but in the past we had always special parts made to the drawing and print. But because the volumes are coming down, today we are trying to use standard parts, especially commercial vehicle, and then trying to accommodate it in the design itself with the complementary parts. Okay. So reduction in number of parts is an example of simplification, and standardization usage of standard parts like fasteners or bearings. That's also an simplification, standardization, which is really going to help to prevent the random failures. So in terms of electronics, combination of logic circuits, multiplexing of functions are also examples. It's quite difficult for us to understand here in terms of the automotive industry for the design for random failure prevention. But some example I'm going to give here as very clearly we will understand the reason for that, and then try to provide a redundant steels, redundant bearings, things like that. So design margins is also an age-old concept, but I'm going to slightly deviate from the typical design margin, bring some statistics into that. The degree of a design margin can be talked in terms of a safety margin. I'm going to explain that. And also the degradation prevention by using a low load use. Okay, so it's slightly confusing. Like, what do you mean by? I would specify the requirement. So you have designed it, and what is the point of degradation of that? It means I have to over design it. For example, if I have to use a product at 150 bar, okay, I will try to use it at design it at 160 bar, 165 bar, and start using it at 150 bar. Conversely, if I design it for 138 bar, but I use it at 138 bar, I design for 150 bar. So this is a very classical example, which has actually helped us in several critical applications in terms of the product derating. But this may be slightly difficult to do it at high volume products, but I will try to make some justification as we go along, as we have some experience on that. Next one, please. And slide 18 indicates some more details of the design aspects that can be considered for a random failure prevention, okay, such as a fault tolerant system, using fail-safe, fail-soft, or foolproof concepts. So some of you may be aware of all these things, but I thought it is important to understand as a condition of fail safe, fail soft. So fail soft is like you can take example of a tubeless tire, so that the tire is going to leak, but then it's not going to stop the vehicle movement. You can say drive for say 100 kilometers, and then the failure is being soft in nature to be allowing us to run it for some more time. This is fail soft. Fail safe, again a very classical example of our own swing gear design. I will again talk about this. Sometimes you have to please bear with me, I may repeat it. Basically, because by repetition, I think you will understand why, what is my mind is thinking about that. In the hydraulic gear, we have the mechanical gear, we have the hydraulic valve, we have the hydraulic piston. So all the three parts are combined: mechanical gear, hydraulic valve, and hydraulic piston. So even in the hydraulic phase, the mechanical portion is going to be available. So hydraulic fails, but still the mechanical gear will be working. So it's a fail-safe design. So it means you can still operate, but with a reduced performance level. So this is a fault-tolerant system with a fail-safety or a fail-soft system. Okay. In terms of the human interface conditions, the interlock for prevention of operation mistake, like for example, if you look at a typical camera system, the flash will not be allowed to work unless the shutter is open. So simultaneously, when you press the flash, the shutter will open. So the interlock is provided to prevent the battery discharge. Okay, so this is something like that. The human interface consideration to be taken care of. There is a battery that keeps draining. Very simple example of try to understand the interlock provision. So some of the examples we have in our own product, I will try to explain. The structure for preventing incorrect assembly, so that we have a proper poke for preventing of incorrect assembly, so that we have a directional available. We have a paper so that we are not able to assemble it in an inverted way. Or we can also use an operational guided display, but is the last one because nobody is going to use the guideline to keep seeing it for assembly purpose. Next slide, please. Yeah. So in terms of this slide number 20, so to recall the bathtub curve, if you can recall, this is the left side of the bathtub curve. Okay, so this is actually an exponential distribution. Typically, the left-hand distribution of an individual, where there is no, which does not wear out. Means wear out, if you recall, it will be having increasing failure rate. So the exponential distribution is typically a simple distribution with mathematics like that. With lifetime of the parts, you see no wear out. There are various types of distributions available, but for example, to make life simple, I have taken only Weibull distribution and exponential distribution in the coming slides. Okay, so that we can understand what's happening in the usage, whether it's a process-related issue or a material-related issue. So in the Weibull distribution, we have all the three failures, like increasing, decreasing, and constant failures. The magenta color, where you can actually see that it's actually a m greater than 1, it's the shape parameter. So when you talk about the Weibull distribution, we have classically two factor or three factor. Here I am talking about the two-factor Weibull distribution to make life simpler. We also have the three parameter Weibull distribution, which then also having a offset parameter, but I am not going to talk about that. Here, when you have n equal to 1, then it becomes exponential distribution. So that is a very useful way of looking at Weibull distribution. As a mechanical engineers and as well as reliability engineers, people are very fond of using Weibull distribution because it makes life easier to predict all the three failure rates with a single mathematics, and then you can look at the various time factors and then decide whether we are in which part of the lifetime, whether they are decreasing, increasing, or a constant failure rates. Okay, next slide. Yeah. So we are in slide number 22. So here we are talking about a gear pair. For example, I have designed a steering gear with a contact stress level. Contact stress is actually going to give about the wear out of the gear pair. For example, if the gear is designed with a contact stress of 2.8 e⁵ psi, the m value is 3.2. So for the same material, so I can now decide what is my Weibull distribution. So typically, I would like to have a low value of the Hertz stress 2.2 e power 5, so that I've got a variable distribution of m equal to closer to 1, means that I will not have any wear out problem. So as a designer, not only the stress level, but by means of making the pass to this stress level, testing out, getting the test data, we can get the variable distribution, decide which one I should have my design guideline for my future design. So it's the example of an 8620 material which we use one of our gear pattern. Okay. Now we are in slide number 23. So an exponential distribution classical example are the electronic devices like transistors, diode, resistors, and conductors, which don't have any failure rate. So either they have got the premature no failure, like I was explaining. Electronics have always a problem of either there is the issue of the raw material or processing issue. Only those failures are there. There's nothing like a great wear and tear happening, and like a mechanical part where you have a increasing rate.
I see that Mr. Tirupati has lost the connection. So, Mr. Sindhuja, Ms. Sindhu.
Yes, ma'am.
Yeah, you can start.
Yes, ma'am. Yeah.
Can you continue from where he left? I think he has just left by mistake or whatever. Yeah.
I think his connection is lost. Ma'am, can I take
Okay.
the electronics reliability?
Yeah.
Because I'm not a mechanical person. So can I take the
Okay.
electronics reliability?
No, I can continue. I just-
Oh, he's come back. Okay, he's back. Okay.
Yeah. So in terms of slide number 23, so variable distribution, the classical examples are the motor bearing, gaskets, cylinders, etc. So mechanical device, I was explaining you, it's always with the variable distribution. Next one, please. Yeah. So as I was explaining earlier, so the bathtub curve itself is not a single failure rate, but it's a combination of 3 failure rates happening for different products, or could be one product. So 0 or to zero less than failure rate, less than 1 initial failure rate. If you look at the green color curve, it's a decrease in failure rate. If you can recall, it's an exponential distribution. The other one on the blue one is a flat curve, the random failure. Explaining it's very difficult to analyze random failure. Typically, it's happening over a usage condition. For example, a tire, when it's going on a pothole, which is very difficult to predict. And randomly, it can happen. Of course, you can tell that in India, in terms of the classical village roads, you can always expect more of such no failures in terms of the roads not good, causing some wear out of over the tire burst and things like that. Other one is a wear out failure. Typically, when it happens, when the parts gets aged. For example, when you talk about 10 years of a product or 15 years of product being used in the commercial vehicle industry, beyond the 10 years, you will start seeing, definitely beyond 5 years, you will start seeing products getting deteriorated, wear out, getting worn out. Like a human being, like the bones gets worn out, the skins gets worn out. Products, mechanical gears always get worn out because of the usage condition, because of the use. So that's a magenta color line is showing increasing failure. So what we really see as a failure combined is the bathtub curve for simplicity of understanding. Here you have to understand that people call it as a failure rate or hazard rate. Okay, so hazard rate is an American term and failure rate is typical Japanese. So we try to follow in India more of Japanese terminologies and more of European and English terminology. So here I'm trying to use it as a failure rate. And some of the journals, when you look at the overseas journal, like American journals, they talk about hazard rate. So don't get mixed up on that. So they talk about the failure rate. Okay, next slide, please. Yeah. So this is the same curve earlier. So the first one is called infant mortality, or the decreasing failure rates, decreasing hazard rate. Second one is a failure not depending on the age, like puncture of a tire or something is happening within 40,000 kilometers. Okay, or something like you can talk. But if you have a warranty policy of 300,000 kilometers, I would expect that the constant failure rate would happen from 40,000 kilometers up to maybe 250,000 kilometers. So this is my guess. Okay, so could happen anywhere in between. But if you look at the tire itself, people don't give warranty beyond 50,000 kilometers. Okay, people think the tire has to be changed. So each of the products in a commercial vehicle have their own failure rates, and each of the manufacturers or the suppliers have their own failure rates because there's a limitation of the product itself. So people are coming with new innovative designs like the tubeless tire is definitely one of them. So instead of not allowing them to, instead of allowing them to run for 100,000, 200,000 kilometers, we are having redundant tires in a commercial vehicle so that even if one goes off, we can run it for some more time. Tubeless, of course, tubeless tires are not coming to the commercial vehicle, but I think it's a matter of time. The tubeless tires also will come in because there is some difficulty in the rim sizes and also the maintenance of the rims because it cannot take a deformation of the rim. Okay. Now the last way, but not the least, is the increasing failure rate. Definitely, this is a wear. Okay. Can you go to the next slide, please? Yeah. So I will explain you about some of the concepts. How in the product life cycle we can take the cognizance for improving the product design, cost, product quality. I was explaining about QFD. I was telling about QFD, not explaining. The QFD is nothing but a quality function deployment tool. It's actually a very powerful tool used by the Japanese to convert the engineering requirement or a customer requirement into a product specifications. For example, if I'm going to talk about, I want the product to withstand I want to use it for 2 times the rated load. I want a factor of safety of 3 times the rated load. For example, bus test, I want 3 times. Okay, what is the minimum voltage I can have to maintain? So some benchmarking can be done. So we don't have enough data, but sufficient information is available. Okay. So don't get me wrong that if I put data not required. Data, I mean extensive data in terms of number crunching. Okay, I'm talking about running some 200 odd information and then generating the classical curves, and then getting the variable plot, and then getting some beach and life and all that. So those type of things are not required. The other one is redundant design. Of course, again here we don't require data. We have some information in terms of benchmarking. And the other one is the FME. FME is failure mode effect analysis. It's a very classical tool being used across the industry. But this is also have some own limitation, where FMEAs are actually more theoretical. Unless the actual failure happens, we don't have the actual information. But somewhere a concept FMEA or a product FMEA will be a useful thing so that we can prevent the failures on a similar products as we mature the design. The next one is the fault tree analysis. So this is also having a very long history being used in the electronic industry, at least 40, 50 years back. But it's very really useful because we have the real life data and being used for the fault tree, and then we are able to understand how to take the inputs of that. The next one is the design reviews. Then obviously we have to the testing, failure analysis and failure tested technology. I'm going to talk about a bit of it in the later slides. I will not dwell here. And production usage in the field, like usage of failure beyond warranty. For example, today we had in the past up to 200,000 kilometers because we had data collected beyond 200,000 kilometers. So customers were able to tell us that okay, up to 300,000 we have no problem, no major problem. So why can't we increase it? So on selected vehicles, people were able to provide 300,000. Now it is becoming mandatory for us to provide 300,000 kilometers of warranty across the product line. So here the failure information beyond the typical warranty is also an important thing to do. If we talk about 300,000, you have to collect information till 500,000. When we talk about 500, you have to collect beyond 500,000. For example, Toyota gives a B5 life of 500,000 kilometers on their own product lines. Whereas Indian customers, we talk about B10 of 300,000 kilometers. So you can understand the difference in the technology of the products in terms of how they are able to provide with a higher confidence base. Basically, they are able to do a lot of work on employing the design concepts ahead of the competition. Next one. So I come to slide number 28. So this is how do you do about improving the product reliability? So very simple, tell like a PDCA concept: plan, do, check, act. So we have to first plan what should be our reliability. So that is we have to specify the reliability. What is the reliability we want? Then we have to design for it. Then test for it. This is the do part of it. Then check for it in the manufacturing. Then and in terms of if there's a problem in the field, we have to work on improve it. So this PDCA cycle is being used across any product improvement whenever you have a difficulty in doing something. So plan and do comes with specification and designing it. Sorry, plan part comes with specification, do part comes from the design and testing, and the check part comes from manufacturing. That parts come from the field usage and the continuous field quality improvement. Next one, please. So now, how to set this specification, reliability targets? So various inputs are available from the customer, OEM, or a program, from the past experience, or the top management. And we require more enough information, more sufficient information like data, warranty data, customer survey data, benchmarking, end user duty cycle, manufacturing data, operating environment, and policy of the percentage, like how many percentage I will allow the defects. For example, we talk about the ITGV, I'm going to talk about the output here in the failure period, failure free period, incidents per 1,000 vehicle, mean time to failure, or MTPF, or MTBF, mean time between failure for the parts which are going to be repaired. In each and like that is 10% of the failure of the life of the. For example, if I launch, for example, 100,000 numbers in a year, I will allow 10% of them, that is something like 1,000 numbers. They have to, all the 1,000 numbers will fail within this. So it means beyond that 1,000 numbers, they have a ditch and life. So it is, I'll explain again in some more clarity later. Now, processes in terms of apportioning, considering of the criticality and the product life cycle costing. So the process, and this is actually given to the product, the process design teams. So the reliability once is being set based on the past experience. Typically, the customer or the top management when launch a completely new program. Okay, I want to have a higher warranty policy. Then probably I will use a higher design specification. Then over a period of time, I will be able to improve the product specification to the customer. Okay, that's how the top management can give a direction at the starting of the design. Next one. Yeah. So, what are the steps of the doing the DFR? Identification of failure modes, preventing them or minimizing them. So, how do you identify the failure modes? So, I've taken only very simple examples here of a DFMEA. FMEA I was telling earlier, now I'm talking about DFMEA, the design failure mode effect analysis. The other one is that the process failure mode. I'm not talking process failure mode, even though that's also to do something with the process design. I'm typically as a product designer, I'm talking DFMEA. And then the fault tree. Fault tree is actually trying to get the actual failed part, trying to look at the part by part, trying to understand what is the failure, where is the failure, what is the components which is failed, looking in more clarity, more closer look from the Gemba, look at the product, the combination of physics of the problem, then really I can understand what has really gone wrong. The fault tree analysis is a very useful tool to identify the failure modes. Now, some of the other prevention mode is to have a stress analysis and parameter design by design of experiment. And then the minimizing failure modes is the tolerance design, designed for manufacturing. I was explaining earlier about the classical problem of using standard parts or made to print parts. Okay, so still a lot of debates go on, but the latest is thinking obvious to make the cost less. People are talking design for manufacturing using standard parts from the big suppliers, using the tolerance design so that we can overcome the failure of the parts by means of taking care of the design itself, so that tolerance can be accepted as it is from the large volume manufacturer of a fastener or a bearing. Now the other one is implementing tendency. So you can you had a very tough discussion with one of my German OEM earlier, friend in the design So we was telling, no, when you have one part which is failing, so how can you introduce two parts? So anyway, they are going to fail. But the point is, we are not going to introduce just like that two parts, but there is going to be some more, intelligence built into it. So I also explained to them that redundancy doesn't mean just simply duplicating them. One classical example of redundancy is to have the twin engines in the aircraft. For example, if one engine fails, the other engine can seamlessly take over. Okay, so it means implementing redundancy also requires some intelligence. So it means we have to predict the failure, or if not, the failure is going to happen. So trying to take care of providing an alternative so that the engine, one engine fails, the other engine is going to start. Similarly, in the mechanical industry, we don't have that intelligence being built into it, but implementation of redundancy could be in a different format. I'm going to explain them in examples. Next one, please. Yeah. So I want to touch upon the manufacturing reliability. So what are the causes for the manufacturing variations or the uncertainty in the parts? So obviously material properties could be variability. Okay. So we don't get all the parts from a single vendor. Okay. For example, I want to buy material, say it's 620 material. There's inherent variability by the design standard. We allow that. Even though the standard allows that, there could be a time that there's no failure from a supplier A, but supplier B is a problem. And then because the inherent variability of the mines from which the parts come or the way in which it's getting processed, there's inherent variability which is just to be allowed from manufacturing point of view. Second one is a lack of insufficient data itself could be a problem. For example, I don't have certain information on the material property, like I want the isoid impact for a heat treated part. Okay, I may not be available having it immediately unless the part is made. So as a designer, that's some problem for me, but it is reducible because after some time I can get the data about it. Now coming to the human error, like you can ask what is the human error metal property? Like there could be some real time mistake in terms of transferring the information from a knowledge base or a database where really we have a problem. Okay, so this could be by oversight. So it requires a design review. So multiple people look at the design calculations and standards. So we are able to get the human error also overcome by means of that. But this is sometimes happens by oversight. But in industry like us, where they've been classically using similar material, I think this could not really happen. But when you're going to new materials, because of want of the customer requirement of contradictions. Okay, when I talk about contradictions, I think I'm not going to leave that. So there's something called a tool called TRIS, which can actually help us to take care of the contradictions. Okay, that I will talk in a latest later at some point of time. Now the other one is the properties with respect to wear. For example, how does the mechanical properties change over a period of time when the material itself starts wearing out, because the surface has a particular case steps after heat treatment. Okay, so if the case step gets worn out, the metal properties change. Okay, so this is really a problem. Okay, problem in the sense like you should know enough information on that. Now the loading, for example, in the field data, this could be really the problem, like human error, lack of understanding of the physics of the problem. Okay, what is happening on the load conditions? How does the load change over a period of time? Whether what my thinking, whether it's a static load, dynamic load. If the dynamic loads, it is a continuously increasing load, reducing load over a period of time. So when I talk about this understanding of physics of problem, I have to tell that when the vehicles were being used for 2 to 3 hours, we don't have the problem in some of the applications. But then if the same vehicle is used for 7 to 8 hours, like that's what's happening in the last, I think, 6 to 7 years, even in India, in passenger car or even commercial vehicle, for example, people are using the vehicles for at least 20 hours every day. You will be mind-boggling to see that. We had some experience in the last few years. Customers are trying to find alternative methods to the air mode of shipment, trying to use a commercial vehicle non-stop, from Chennai to Mumbai in 24 hours. Okay, like that they're trying to give advertisement so that they can actually beat the aircraft, means the cost of flying the part, not driving the part. So they've got 3 drivers or 4 drivers, because driver cannot drive beyond 4 hours or 5 hours with that complete attention. Okay, But as the human are subject to error, they are at least able to have 3 to 4 drivers over a period of 20 hours. For example, if you look at some of the expensive buses, like people are using 2 drivers, used for 6 hours. Okay, like Volvo bus, you can look at the 2 drivers for a overnight journey between Chennai and Madurai. Chennai, Trichy, for example. No? Today, Trichy, Chennai is just 4 hours, so but there's no need for a multiple driver. But Chennai, Madurai, it's 7 hours, so people still require maybe 2 drivers. 4 hours, they're able to manage. So this is an example of a classical loading issue where we have to have the understanding where we are continuously loading, or so this is going to help us to make the life easier when we start designing it. And the other one is the boundary conditions, lack of understanding of the boundary conditions. So what do you mean by boundary conditions? For example, I'm on a truck on a hilly terrain or on a flat road. So the boundary condition of the trucks also lack understanding. We think that 95% of my vehicles are being used in a flat road, but then we start getting problems on a hilly terrain. Okay, so the lack of understanding of that particular testing to be done even for that 5% of the vehicle population was probably left out by the OEMs and as well as by the Tier 1 suppliers. Then we started getting the problem of warranty issues. So this was really one of the problems we had in the last 2 years, to which we could actually, with a lot of time and money spent, we could actually do it. But it's very tricky. So there's a learning curve for us in terms of trying to understand what can be done for the boundary conditions to be understood. So we really have to run in the real life conditions and then probably have sufficient representation of what's happening in the field. Next one. So when we come to reliability predictions, please. So I'm giving a classical example of a spring here. So you can just give me a minute where I wanted to understand what are the different causes for the failure. Okay, the different failure modes are like a fracture where a loss of spring rate. Looks very simple, isn't it? The failure mode. Failure mode is what we can actually see. Okay, what we can, as an end user, okay, it is fractured, broken, it's worn out, spring is lost, spring tension is lost. Now, what are the causes for them? If the fracture itself could be because of the material defect, so now you can recall this material defect could cause a reducing failure rate. It could be a starting problem like decreasing failure rate. You can recall that raw material problem will typically result in a decreasing failure rate in the part of the Barter curve. Okay. Now the hydrogen embrittlement is again a process. So we had a classical example of this hydrogen embrittlement in some of our fasteners, because when the part is getting heat treated, we have to do the hydrogen de-embrittlement process to be followed so that the crack doesn't happen on the part. But if that happens, it's very difficult to notice on the physical part. It will actually result in the crack or a fracture over a period of time. That is within 24 hours of usage it's happening, but it's very difficult to see them with the naked eye or even a microscope or your fracture equipment unless you have started applying them on the load condition. Okay, so no surface roughness be another failure cause, misalignment, the way in which we assemble it could be a problem of the fracture, excessive loading. So you can look at, when you look at even a simple part like a spring, the failure causes are at least you can look at 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 causes of a failures. Of course, I've grouped it for a sake of understanding here. So you can look at the material defect can cause again wear, but it is over a lifetime, so it's going to be a increasing failure rate. Again, improper surface finish, the finish is not sufficiently good so that the contact stress I was explaining earlier in terms of a particular material. So also could be because of the surface finish or misalignment, which can cause a wear. So just want you to understand that it is going to be so much of things to be taken care by the designer in terms of proper design standards, design guidelines, and then the previous experiences are going to be of paramount importance for us to avoid those failures repeatedly happening on that. So there are a lot of standards on the design of springs. But as you look at a design standard for a steering gear, I think we have evolved over a period of time. What needs to be, which is a typical failure part, how to take care of them. Next one. Next one. Indija, are you there? Please move there. Yeah. So I was trying to explain you the factor of safety earlier. For example, factor of safety means we have to design the material to withstand a stress. Okay. Normally, a safety factor is considered a deterministic value of a stress in the part against the material strength. In reality, they are random variables. So, I explained earlier, the stress and the strength are not a straight single point. Okay, they are not a single deterministic values. So they have their own curves. So imagine here there's an overlap. Okay, so the intersection is actually there's a zone of failure. So that can be calculated by using a simple mathematics formula here, safety margin, by means of the difference between the stress and the strength. Strength is the material aspect. Stress is what is actually happening by the application. So with respect to the variability, we can actually get the safety margin. Ideally, we need to improve the safety margin. We want to have a very low value of that. Actually, we want that value to be 0. Okay, so we need to have a very large amount of factor of safety. But then, because of the expensive nature of the material, sometimes we are forced to have a very close factor of safety or a safety margin. So you can imagine that in an automotive industry, we are not looking at a factor of safety of 2. We are looking at 1.7, 1.8, sometimes 2, 2.1. But then that is all we have the standard. So in terms of the stress and the strength. So maybe very strange, but then that's how we are operating, because we will otherwise make it non-competitive in terms of the market, the competition, that we'll have a large, very big steering gear, very big shaft, lot of multiple seals and all that. So we are trying to be competitive. Automotive industry, because of the volumes, we need to be competitive. This is inevitable to have a safety margin considering the distribution. Next one. Yeah. So this is some examples of the stress and the strength data. The stress, we are talking about the mechanical stress, tensile, or a compressive in nature. Strength, we talk about ultimate tensile or a yield strength, the different types of strength. This is the design factors that affect the stress, for example, also could be due to cyclic load, duty cycle, speed of operation, while factors that affect strength by the geometry, by the number of teeth, lead, pitch, profile, error is specified in the drawing. So definitely we have to take care of both aspects, how it's going to be used and how it can be determined in the application. So if you look at the stress, for example, corrosion stress, the strength could be the coating thickness, the corrosion resistance, or the material property. So this has to be taken care. The wear or a pitching contact stress, this has to be taken care by the contact strength. Next slide, please. And then in terms of the duty cycle, cyclic load, speed of the operations, aging, that's some of the stress-related aspect. Strength could be heat treatment, dimensional assembly process, variations, bending strength, etc. So strength is specified and built into the design, and the stress is developed during usage. Strength is obtained during the lab test. Stress is obtained in usage condition and usage profile that should typically represent 95%. But I think with my recent experience, I think 95% users are not enough. So we should look at 99% of the users so that we reduce the warranty cost. Now, last but not the least here is to emphasize that the simulation, like Monte Carlo simulation, can be used to evaluate the stress and the strength distribution for obtaining the life of the distribution. Like I can specify the curve itself, like, okay, this is a normal curve or a normal distribution with what is the variability of that, so that we can actually estimate the amount of overlap. So if you recall the stress and strength curve, factor of safety or the design margin I was explaining earlier, we can actually do a Monte Carlo simulation. So by means of latest tools, we can actually predict reliability. So it's very, very funny that we can, how do you do prediction of reliability without actual testing high volume. So I think our computer engineering comes in to help by use of tools like Monte Carlo simulation. Some of the designers, some of the people are familiar with this Monte Carlo simulation. So it's a statistical way of giving the variability, giving a random number generation, creating the profile of for example, I want to generate 200 random numbers between this to this with a variability of a normal distribution. I can get a curve. Okay. So with that curve, I can actually get the real-time factor of safety. So which can really help me to tell, okay, whether that's good enough or I need to improve something else in terms of the safety standards or strength itself. Next slide, please. Yeah. Human interface reliability, I was talking earlier again. The foolproof, fail-safe, fail-soft. Foolproof is the process is designed such a way that the process itself is not allowed. The activity of negligent performance, which becomes the cause of failure, is not allowed to happen. So, classical example: camera, shutter, and a flashing device. That's a foolproof. I already told this example. Next slide, please. Fail-safe. So, re-emphasizing here, even if it fails, it will work safely, allowing the system or the component to work with limited trouble or limited performance even after the failure happens. Like hydraulic steering gear with a pump failure, gear can work in a mechanical mode. I explained earlier. The hydraulic gear is a combination of mechanical gear with a hydraulic valve and a hydraulic piston. Fail-soft is like a battery. Okay, battery in automobile. Battery in automobile doesn't go off suddenly. Okay, it wears out. It starts discharging slowly. Because it's strange that during my experience in a car, the battery suddenly went off. Okay, I think I was quite unaware because the maintenance of the battery was so good that it suddenly failed one day because it crossed 4 years of its life, and suddenly I could not start the car, and then found that the battery was completely drained. But normally battery what happens is you get some starting trouble. Okay, then you get the starts, light gets dim. But with the improvement with the battery technology, I guess fail-soft design in batteries is getting into the highly reliable in nature. But tubeless tires is another classical example. I already told that it occurs very slowly. You can actually use the vehicle for some more time. Next one. Yeah. Now test for reliability. How do you estimate reliability? So without testing, you cannot really get the reliability curves, reliability value. So you have to use practical usage tests or accelerated durability tests or special environmental tests, like to simulate the field or a drive condition. In the lab, we have to use a bench simulation or like a engine bench simulation test or a lab bench. For example, steering gear using a bench simulation test. It's a system, like steering gear and hydraulic pump we put together and then test it like in a system. The part we also do like the rubber parts accelerated lifetime test, compulsive degradation test like high temperature, okay, like part reliability test, or a low temperature with contamination. So it's a degradation test typically to take care of the environmental aspects. The material test is another important area. For example, lab test on the metal property itself can be verified. Next. I was telling about the beach and life. So if you're able to plot the life parts of the gear as you get worn out, so you can get as the numbers keeps increasing with respect to time. This is not the failure rate. This is the failure. Okay, so this is not a bathtub curve. So you don't get confused in that. So the area under the curve, beach and this is like 10% of the population actually are failed. So we might use special probability papers to estimate the beach and life when you have got limited information. At least we have to have 5 numbers. Our guru, Dr. Washi used to tell that at least 6 numbers to 10 numbers is a good time to test at a component level to get the beach and life. But the OEMs try to do 20 numbers, 30 numbers, but some of the fast car customers, as explained you, they do up to 200 numbers of this, try to get the beach and life. Next one, please. So reliability estimation is done on a new product in order to predict the field quality. So judge whether the field quality achieves the target. For example, no failure up to 3,000 hours of operation in the lab or in the field. So laboratory tests should be conducted. does not achieve the target, some design changes must be done. So this is a classical example. If the product is not achieving that reliability target, what to do? Typically, as a designer, I would tell, okay, we have to improve the process. But okay, Dr. Washer used to tell that if something is wrong with the testing, and you are as a designer doing it, I think what is under your control is the design. So you should do some changes in the design. So so let us not talk about the product life cycle itself, where we already told that 80% of that cost is being taken care by the product they design. Obviously, the place where to improve the design is also on the product design than on the process design. Usually, lab tests will be conducted at the proto stage or in the trial run, so that we get a good correlation of the actual field data and the proto data, so that can be extensively used for future products. Next one. Okay, step one, to find out the proper lab condition so that we have the same failure mode. So this is very important. For example, I have a C failure, so my test lab should also have the same failure. I should not get another failure mode, so then it is not of any relevance to me. Failure mode should be the same. There must be a correlation between the field tested data and the lab data in terms of the slopes. The product must fail or suffer the critical failure mode in a specified period of time. For example, in the lab, you should fail within a week, 2 weeks, or within a month. The proper lab test condition is actually found out through the trial and error. Very difficult sometimes. But having said that, the experience accumulated by the industries, so we have classical test conditions evolved. So with that, we are able to get the proper lab test condition. We have got standard lab tests being used to predict the lab failure modes, then try to see how we can actually correlate to the field test. Field failure, typically in hydraulics, we have the seal leaks, we have sometimes the noise issues, and very rarely we have got a classical breakage problem. Okay, because the design is very quite matured the last 40 to 50 years. But this is tricky in terms of the noise and the leakage, where we are trying to improve the currently the reliability. Next one. So this is a classical example. Product one, the beach and life is 50 hours, and the field data, for example, is 115,000 kilometers. Okay. So second one is product two. The beach and life is 10. The beach and life is 35,000. So if you look at, there is seems to be some correlation. Like there's a factor of 30 in the first one. There's a factor of 35. Now when you do a product three, you go to the next slide. Okay, beach and life is 200. So typically based on the previous experience, I can give a beach and life of 60,000 to 90,000. Okay. So this is how the field quality is predicted with the lab test data. So that's what my thinking of how to go about improving the product reliability. Definitely, we have to specify the beach and life. You have to do both the lab test and the field test of the past information, and then try to predict the future. Next one. Yeah. So lab test should be carried out for a new product, but also on a new subsystem or on a new vehicle, OEM level. Okay. So that only then we get a complete information of what the typical failure means. Next one. Yeah. So before I hand over to Sinja for another 10 minutes, I'm going to talk about some of the evolution of reliability and some of the other classical information on the literatures on this. The reliability prediction model was started as early as 1940s, and it is continuing very strongly with the usage of reliability simulations using Monte Carlo as giving example, especially the electronic industry started getting the physics of failure models into their own mainstream. So this is how it has migrated in the last 60 years. I don't have enough information beyond 2000 because as reference I have up to 2000. So if you can look at the various industries like telephone industry, then aeronautical industry, nuclear industry, electronic industry, then it is clearly that wherever there is a human life was involved, people are giving more importance to reliability. But from more than that, now it has come to the automotive, especially safety critical. It's also causing a concern in terms of any safety criticality to the human, not only the driver but also to the pedestrians. So I think we are on the right track of trying to use the reliability methodologies, trying to use it for the automotive industry. Next one. Yeah. Sindhija, can you continue? I will take again another 10 minutes later.
Yeah, okay, sir. Good evening to all. I hope I'm audible to everyone. Yeah. Thank you, Adam sir, for this opportunity. Today, I'm going to give a glimpse of reliability in electronics in the upcoming slides. So I'm moving to slide number 54. So as we all are aware, the electronics industry has grown drastically over the last few decades, especially in the automotive industry. In the golden old days, the cars like Ambassador and Fiat had only the mechanical or the hydraulic system, and the only electronics available in the vehicle may be the radio. But now, almost all the vehicle having the controls through the electronics. Even a simple low-cost hatchback car contains at least 5 to 10 ECU, basically for engine, for steering, braking, window, and infotainment, in which many of the systems are a safety critical. Example, steering and braking systems. In the system, the safety is critical, so obviously the reliability is paramount. So I'm moving to slide number 55. So back in 1990, the General Motors, Ford, the Semiconductor Council, GE Tech created the Automotive Electronics Council to set a standard for temperature and pressure resistance for the electronic components to ensure the consistency of the safety specifications. So as per the standard, the AEC Q100 is for the integrated circuit, example, microcontrollers, gates, APOMs, drivers, and other the power controller ICs. The AEC Q101 is for the discrete semiconductors, example, MOSFET, transistors, FET, etc. The Q102 is for the discrete optic electric semiconductors, for example, the photodiode and phototransistor. The Q200 is for the passive components like resistor, capacitor, and inductors. To summarize this slide, the automotive industry started to use the AEC qualified components to simply increase the reliability and safety. I'm moving to the next slide. So as we all aware, the vehicle environment is very, very harsh environment. So the semiconductor components are prone to high level stress in terms of high current stress due to the transient current surges, high voltage stress due to the transient voltage surges, obviously a high temperature stress from minus 40 degrees Celsius to 155 degrees Celsius for the engine compartment electronics, high shock and vibration stress, electrostatic stress, electromagnetic interference, and finally contamination. I'm moving to slide number 57. So these slides will give you a clear view on automotive electronics requirements compared to the industrial and commercial electronics. If you see the temperature, the consumer electronics are operated in almost the room temperature. But on the other hand, the automotive electronics is operated in the temperature of 155 degrees Celsius. Then if you see the operation time or the lifetime, the automotive industry vehicles are used for the at least 10 to 15 years before it end up in the scrap yard. And the expected warranty is around 5 years, which is much higher than the commercial and industrial electronics. Meanwhile, the automotive industry is having a very stringent standards for failures. So the failure is absolutely intolerable. So the target for the failure rate is always 0 ppm. Since all the vehicles are having, is going to run at least for 15 years, the customers are expecting at least 15 to 30 years of supply of parts. I'm moving to slide number 58. This is the example of the temperature requirement. If you see the consumer electronics, the temperature increased from 40 degrees Celsius to 60 degrees Celsius in the period of 20 years. As for the automotive electronics, the temperature rises almost 100 degrees Celsius. The main reason for the temperature rise is the ECU were mounted and the chassis or the underhoods, which increase the temperature requirement. The second reason is the high loads are connected to the controller and the higher number of components are integrated into the controller into the smaller packages, and the entire ECU is built into the actuator itself. It will increase the temperature requirement drastically from 55 degrees Celsius to 155 degrees Celsius, as high as 155 degrees Celsius. So I'm moving to slide number 59. So in this slide, you can see the three different topologies. The first one is the remotely mounted ECU, in which the silicon is separated from the actuators. So the junction temperature TJ is nearly 150 degrees Celsius. In the second topology, the ECU is fitted adjacent to the actuator. Hence, the junction temperature of semiconductor can rise up to 175 degrees Celsius due to the heat radiation from the actuator. In third topology, the ECU is built inside the actuator, so the junction temperature rise as high as the 210 degrees Celsius due to the direct heat conduction and radiation from the actuator. So this is the mapping of the temperature to the vibration requirements for the automotive electronics. The electric power steering, EPS, is what we are currently working. For EPS, the temperature requirement is almost 125 degrees Celsius and the vibration requirement is almost 30 G. So we have to design the electronics, that is the ECU, by considering the stress level for the better reliability and safety. Moving to slide number 61. So as I said, in previous slide, this is the example of the EPS in which the temperature requirement is 125 degrees Celsius and the vibration requirement is around the 30 degrees Celsius. So the temperature and vibration requirements has been taken care of by means of the automotive specific technologies like direct bonded copper or binder clips or a low temperature co-fired ceramic technique in which the entire electronics is built over the copper substrate. If you can see the copper substrate here. So the entire electronics is built over a copper substrate, and the bigger components like common mode choke, differential mode choke, and the capacitors are horizontally mounted and binded by the special binders and adhesives. With this, we can achieve the temperature up to 125 degrees Celsius and the vibration level up to 40 G. And I'm moving to the next slide. These are the reliability prediction guidelines used by the various industries. The first one is the MIL HTBK 217 standard from the defense industry. It's a very widely used standard. The second is the Bellaco TR 332 is for the telecommunication industry, which is very similar to the MIL HTBK 217. So the other one is the RDF 2000. This is the latest and most comprehensive European methodology developed by the CNET. The PRISM is a new technique developed by the Reliability Analysis Center, which has the ability to model the thermal cycling and dormancy. Now moving to slide number 63. So the physics of failure is a family of approaches, differs significantly from the other empirical methodologies listed above, and is used primarily at the sub-device level during the design stage. The IEEE Golden Book, that is IEEE Standard 493 1997, is the recommended practice for the industrial standard. And I'm moving to slide number 64. In this slide, it's just an overview how the reliability has been predicted as per the MIL HTBK standard. So the standard gave two different methodologies for the reliability prediction, namely part count method and parts test method. The part count method requires very less information, that is how many parts is being used in the design. So that is the information that is all the required for the part count method. This has been carried out this has been carried out in the initial phase of the design, where you don't have much information and detailed design. So in this method, the total failure rate is calculated by simply summing up all the individual components failure rate. I'm moving to slide number 65. Okay, on the other hand, the parts test method is used in the detailed design stage, where you have the complete circuits and schematics. So the total failure rate is calculated by taking account of electrical stress and the temperature stress of the individual component. So thank you. I just finished my topic. I request RMT sir to continue. Thank you.
Yeah, thank you, Sandhya. Can you continue the slide? Yeah, this is on the publishers of reliability articles, the transactions on reliability, which started as early as 1952 to the Journal of Quality and Reliability by Hindwai Publishing in US 2008. So these are the list of publishers available for us to look at for the reliability publications. Next one, please. This is the select list of the conferences. So we can look at some of the websites of RelaSoft, International Applied Reliability Symposium, International Reliability Conferences by IITs, and also the Annual Reliability Maintenance Symposium. For sake of completion, I have given the list of papers and conferences where you could find more useful articles on how academia has used the reliability as a way to improve their research. Next one, please. In terms of the failure database, there are multiple databases. Definitely more is available for electrical, electronic items, and more of mechanicals are coming from the military standards and also from the Reliability Analysis Center. So if you look at the International Electrotechnical Commission standards of Switzerland, you've got electronic components standards available. Some of them are from IEC standards, and some of them are some handbook, military industrial data handbooks. So where a lot of the American military have developed the standards, mill handbooks, which are used for electronic equipment, could be outdated, but the concepts are there. So you can take them, look at them, see how it can be used for our own application, like simple items like the semiconductors of the common mode choke or some resistances or capacitance, things like that. But more information is available from the particular from the semiconductor manufacturing companies for the chips. Next one. So in terms of commercial available software, we have some experience using RelaSoft for the accelerated life testing, reliability prediction, reliable analysis. Even though I think as a beginner, it's better to use the manual methodology of a graph paper to understand the dynamics of the reliability predictions. But then as you mature, you can use RelaSoft. RelaSoft is available, not very expensive. Maybe I think it cost something like 1 lakh or 1.5 lakhs is what I remember. Very long time back we bought that. But definitely you should have some understanding with them for a academic purpose. This spectrum item software or some of the other things which are being used as reliability prediction tools. Next one. Yeah. So this is my last 2 slides. I'm going to talk about how we have taken care of the reliability in the actual applications. So one was product derating. I was explaining you long years of manufacturing of the process helped us to take care, because when we had the technology transfer from the US to India in 1985, the full production started in 2000 only. So almost 13 years we had, because the factory was established by 87. So, and then we used to localize part by part of that. So at that time, we could not use all the parts to the full specification, because we had to mix and match of the imported parts and the local parts. So what we were trying to do is use the derating to our advantage, use the product design for 150, 138 bar to 100 bar levels. And then over a long period of manufacturing, we use it. And even the last 2 years back, we did one product designed for 150 bar, launched it for 138 bar, and then the last year we launched it for 150 bar. So the derating is really one good terminology, one good technique to be used. Design standards. So this is another example I wanted to share here. We had a design from collaborators from France. So we had nitrile rubbers in that. All of them are imported at that point of time. And I'm talking of 1995, 97. So something like 20 years back. So that was good enough for that applications of 3 to 4 hours of running. But then the same gear was used by the OEMs in countries like Thailand and also in countries like Spain and Italy. So we had a lot of sea leakage. Then we found that the design standard was not suiting for that particular temperature application because with the temperature change, the seal fit really changes. The interference levels are changing, stretch levels are changing. Okay, so we found that the rubber is getting expanded, the seal fit is getting changed. That the seal fit levels was getting changed. So it was actually overfilling it, and it was not breathing. Okay, so we had the wear out of the seal. So we applied the design standard for that particular thing. No, improve the design tolerances, then we could overcome the problem. The other one was better manufacturing process itself was improved by using the alternate design. For example, we moved from an induction hardening specification to a case hardening specification in a couple of parts. Basically, induction hardening is more tough, difficult to maintain. The machines are not very expensive. Obviously, they don't last longer. They last only for 5 years. Whereas case hardening machines are very expensive. They're part of the heating condition. They last 15 to 20 years. Okay, so they are more robust in terms of their operation. So we migrated the parts from induction hardening to case hardening. Redundancy, we had another classical example of a seal inadequate in terms of the leakage because we had a dual bearing in the gearbox. A loss of lubrication during the alternate bearing, we were not able to provide that lubrication. Okay, so what we did was we provided an additional seal closer to the lubricated portion, so we were able to overcome that. So this took us a long time to really understand what's happening on that. Okay, design enhancement, like for example, you have a bolt and a nut, you have to provide a sufficient length of the bolt to avoid that nut having the loss of contact. So this was another area which we improved in our product to improve the water ingress into the steering gear. The other one is use of a design guideline. For example, we are using the positive pressure head in the hydraulic pump to avoid the cavitation noise. I was explaining that the seal leak and the noise is a real problem we face. So I was explaining about the leakage to here failures overcome. The positive pressure was possible by means of improving the CAE prediction. So beyond the point, we could not overcome that because of our mental thinking that we can't design, we changed it. And what we did was we had a lot of requirement coming high capacity pump. So we provide an angular hole to increase the pressure from a negative pressure to a positive pressure, a non-classical way of thinking. So we were able to use the design guideline, usage of that design guidelines to improve the cavitation and noise. Next slide, please. So material change was another methodology we used. So the housing bore wear, I was explaining that if you recall, the decreasing failure rate, typically the raw material was the issue. When we moved from 138 bar to 150 bar designs, so we changed the material basically to improve the housing bore wear, obviously also to improve the strength of the part, the bore, the strength of the part. Understanding the physics of the problem, I have another example is we had two bearing suppliers. We had one from China, the other locally from India. So because of tolerances, we were having to introduce a washer to avoid the seal dust lip of the seal penetrating to the bearing ID. Now, assembly process itself was improved by the design. Manufacturing process improvement by design, I told, from heat treatment, induction hardening to case hardening. Assembly process, we moved from a three-piece steel design to a single-piece design standard. And then another example which I wanted to tell here is a bearing usage of the classical standard bottle parts. So we had to bearing movement. Initial samples were made we could not get the limit samples of the bearing. So then we modified the design to make the parts to the limits of the tolerances. Then we improved that bearing fit to have a higher interference itself to prevent the bearing movement. So these are some of the examples we have applied the methodology, applied some of the tools of prediction. Then after the improvement against the prediction, what's happening on that, then we have overcome the problem. I think we have come to the end of the session now. Yeah. So thank you for your patience. I think we have spent almost 1.5 hours on this session. I hope it was interesting and useful for you to get some idea of what we do in the industry.
Thank you,
Question?
Doctor. In fact, at the beginning, I think you had a doubt if you would talk for 1.5 hours. It's exceeded the scheduled time. I have a couple of questions. So one of the persons, Tenmuri Vendilaman, has asked, do you use X-rays for testing inspections? I'm not sure. It was posted quite early in the speech. So like at around 4:17, she has posted this. So can you let me know, is any X-ray being used? Madam is actually the principal of 2 government colleges, sir. Madam Tenmuri is here. Her video is on. Madam, can you specifically state your question, madam?
No, I can understand.
Yes, ma'am. I just
please.
want to know if X-rays are being used in running for inspection purpose.
Okay, I can tell you that it is not 100% or like even during development. Only if we suspect there's a porosity in the casting, we used to go for testing them by the X-ray inspection. Otherwise, what we really do is to take the cut section of the samples. We have a design standard telling where is the porosity, what the type of porosity allowed or not allowed. But if you're not able to get those porosities in those places and still we have a problem of leakage, we used to go to the X-rays. But the X-ray is not specified by us in the normal design guideline, like unlike radiograph inspection for the welding or other precision castings, because this X-ray is very expensive and automotive cannot afford that. That's a simple reason we are not specifying that. But as a problem solving, really understand the X-ray is being used. Unlike the welding WRA where they use 100%, I think the welding inspections by X-rays. Hope I answered your question.
Yes, sir. Yes, sir. Thank you.
Thank you so much. And then there is another question which says, what is the difference between active and passive components? I think this is related to the presentation when Sindhuja made. So, Mr. Kadiravan, you can unmute yourself and ask. Sindhuja, you're on the line.
Yes, ma'am. The active components, or the example for the active components are diode and transistor, which is we need an electric power supply to operate the device, so it will active only the power supply is given. So the active components, or the best example is the transistor. So it will act as a switch only when the power supply is supplied. The passive components or resistors, it will not need any power supply to act as a resistor. So this is the difference between the passive and active components.
Oh, wonderful. So actually, I should thank all the participants as well for going through this very technical presentation. I'm sure your interest have got kindled in terms of how product is being designed and taking us through the various stages of design and then through reliability. If you have any further questions, you can please type it out, or I will ask Dr. Joshua to wind up. As it is, thank you, sir. Thanks, Sindhuja, for the explanation. Yeah.
Thank you.
Thank you, ma'am. I deem it my privilege to share the vote of thanks for today's session. With a delightful heart of gratitude, I express my sincere thanks to our speaker, Dr. R.M. Tirupati, for enlightening us with great insights on design for reliability. Thank you, sir. Special thanks to Ms. Sindhuja for sharing insights on the electronic reliability part also. Thank you, ma'am. I thank our moderator, Mrs. B. Rajalakshmi, for her support in coordinating the Q&A sessions nicely. Thank you, ma'am. I express my sincere thanks to the management and members of Rane family for their support to Rane Polytechnic for successful conduct of this webinar series. Finally, all these would not have been possible without the participation of wonderful faculty from various institutes. members of industry, and students of various colleges. Thank you all. Do join with us tomorrow at 6 p.m. for yet another talk, which is a interesting talk on Here Comes 5G, Impact on Businesses, by well-known ACM speaker, Dr. Sundar Vedantam, Director DCG of Intel Corporation. So meet you all over there. Thank you very much.
Thank you, sir. Thank you once again.
Thank you.
Good evening, and let me. Thank you so much. Thanks, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, ma'am.
Thank you, sir.